To Trig students, it is Tuesday, March 5th, and today we are going to talk about exponential growth and decay. We're going to continue on with the conversation that we had yesterday about how we can compare linear growth, which is constant, to exponential growth or decay, right? You also have linear decay as well. And really, yesterday we tried to focus on this idea of how do we pick out the differences, but today we're going to expand on that, and we're actually going to learn how to build a model. So if you weren't in class yesterday, I highly recommend taking a look at that short 5-minute video that we watched at the beginning of our notes, making sure that you take your notes and then follow along with this video as well. Later tonight, you'll have a homework assignment that the sub will pass out to you. It is due on Wednesday, and we will go over it together on Wednesday and take questions before we keep practicing exponential growth and decay. So if we take a look at this first example, it looks like we're taking a look at some bacterial growth, right? So if we take a look at time, and notice that it says time is in hours down below. If we take a look at this information, it looks like when we start out that at hour 0, our population is 100. So you can say that that's like 100 microorganisms, 100 populations of bacteria, whatever the case might be. And then after hour 1, it bumps up to 200. And after hour 2, it bumps up to 400. And after hour 3, it bumps up to 800. So it looks like we are adding 100. It looks like we are adding 200. Okay, it looks like we are adding 400. And then obviously we have these ellipsis signs, and then our goal is to figure out what n is. So like, what is that rate of change? Is it constant? Is it not? What's going on? So if we take a look at the questions, it says, what is the initial population of the bacteria? That would be 100. And you can just say 100 population because we don't actually know what kind of bacteria is this. Is this a microorganism? Is this a microbiome? Is this just like dirt? Is it a fungus? Like, we don't actually know what this is. So we're just going to label it as 100 population. Now, is this constant growth? Well, the answer is going to be no. And the reason why the answer is going to be no is because each time it changes. 100, 200, 400. It does not actually constantly increase by the same amount. So we're going to say that this is no. And the reason why this is no is because it grows at a different rate each hour. Now, what we do know, though, what we do see as constant is this idea that, like, if we go from 100 to 200, 200 to 400, 400 to 800, 800 to 1600, and etc., it does look like this is doubling in population. So I'm going to put that in red up here. So if we wanted to describe the rate, we could say that we see that this doubles in population. Okay. And if we wanted to create some sort of model for this, we can go back to that video in our notes from yesterday where we learned that all of these exponential models start off with an initial value. It has that multiplier, which the video speaker referred to as D. And we could say that, all right, well, if our initial value was 200 and we know that this is doubling, X could then be our number of years, or in this case, our time in hours. So X would be our unknown, our time. So when it refers to our curriculum here at Wheaton North, the textbook that's linked in Google Classroom, I know we might not use it every day or really use it in the class itself, but like the textbook gives us this example right here as the equation, right? So y equals a times b to the x power. So this is the same equation where our a value is our initial value. Our b value is the multiplier. And x is the unknown. So time normally, right? So there's a few different ways that we can talk about exponential models. A lot of the times we talk about them as growth, a lot of the times we talk about them as decay. So how do you know what the difference is, right? When we talk about a multiplier that's bigger than 1, so for example, you have a multiplier that's 1.5, 2, 4, 8, 4/3, 8/5, etc. That is always going to be an example of growth, right? When the multiplier is bigger than 1. And what that exponential model looks like, and it could be obviously varying in details, but it's going to look something like this that just rapidly increases and gets bigger and bigger and bigger, right? Now, when we take a look at a multiplier that is less than 1, we are going to talk about this idea of decay. Now, it's super important to make note that even though your multiplier is less than 1, it is not a negative value. So for instance, we can have 1/2, 0.75, 2/3, 1/4, 0.2, etc., right? So again, A and D are interchangeable, right? B and D are interchangeable. In the video we watched yesterday, we looked at a model that looked something like this. When we are now taking our notes from today, we're looking at a model that looks something like that. But the idea that your A is your initial value, whether you want to call it B or D, that is your multiplier. And then that X value is that unknown something that you are evaluating, right? So if we take a look at these two examples down below, like what is the difference about this? Now I know this looks funny typed, but really we're comparing y equals 1/2 times 2 to the x power versus y equals 2 to the 1/2 power raised to the x power. So if we're comparing this, we don't really care about the initial value. The initial value could be negative, it could be positive, it could be small, it could be really big. But what's going to tell us the most about the data and how it either grows or how it decays is going to be that multiplier value, right? So because our multiplier is 2 in this example, this is going to be a growth, right? It's bigger than 1. And because this multiplier is 1/2, this is going to be a decay. It's still positive, right? Like it's not a negative value, but it is less than 1/2. Therefore, your data is decaying, right? So let's take a look at examples A through F, right? Now remember, based on how the equation is written, you want to make sure that you're always looking at the number that is attached to the exponent, right? And our exponent is x, but you don't want to be looking at the initial value, just the value that's associated with the exponent. So for us, our value would be 2, 3, 0.8, 0.5, 1.7, 1.07, and then 5/3. So all of those are the multipliers here, right? So if we take a look at 2, 2 is greater than 1. So this is an example of growth. 3 is bigger than 1. 0.8 is less than 1. 0.5 is less than 1. 1.07 is bigger than 1. And 5/3 is also bigger than 1. And there you have it. How to identify a multiplier. All right, so let's move on to the next page. Hopefully we are feeling good about this so far. So now, how do you find the multiplier, right? Like, how do you know what that actual rate that it's either being multiplied by or changing exponentially? Like, how do you know what that actually is in the equation or how you found it, how you write it, if we're just talking about percents, right? So let's take a look right here. If we are looking at something that grows at 5%, you always have to bring that back to a decimal, right? So you can bring that back to a decimal by taking 5 divided by 100. We know that that's 0.05. Or you can think about moving the decimal places to values. So how do we manage a 5% growth versus a 5% decay? Well, let's think about an idea here, right? If something is doubling, and I'm going to draw some notes up at the top. If something doubles, we go from 2 to 4, 4 to 8, 8 to 16, and etc. And we say that the multiplier is 2. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. Okay, but why is that? If the multiplier is 2, that means that it's growing at a rate of 100%. So how do you get the number 2 from your initial value to your new value, right? Well, let's start with the number 1. If we start with the number 1 and we grow at a rate of 100%, we then get the number 1 in return. 1 plus 1 gives you 2. Okay, let's try it again with tripling, right? If something triples, so I'll draw a line like that. If something triples, our multiplier is going to be 3, right? And we're looking at 3, 6, 9. I'm sorry, I'm adding 3. Oops, see, linear mindset, right? We all have that 9, 3 to 9, 9 to 27, and so forth, right? We're multiplying by 3 each time. Okay, well, how does this actually work? How do you get the number 3 to 9 to 27, right? Well, we actually would say that this grows at 200%, right? And here's the prime example of that. If you start with the number 1 and you grow at a rate of 200%, 1 plus 2 gives you 3. So there you have it. You are multiplying by 3 every time. So if we want to consider a 5% growth versus a 5% decay, you always want to include this idea that your initial value is always going to be the number 1. So we're going to say 1 plus the growth rate versus 1 minus the growth rate. So for instance, when we always say that if something's growing, your value is going to be bigger than 1, our multiplier in this situation is now 1 plus 0.05, which simplifies to 1.05, which, if you highlight that, that is bigger than 1. Okay, if we take 1 minus 0.05, that gives us the value of 0.95. And if you take a look at that, if we're talking about decay, that is less than 1. So greater than 1, less than 1, still working with percents here. So let's try a few, right? So for instance, if I'm saying that my money in my savings account grows at a 12% rate, what is going to be the multiplier in our equation? Well, we're going to take 12%, which is 12 divided by 100. That's 0.12. We're going to add 1 to it, and we're going to say that our multiplier is 1.12. If there's a 7.5% decay, that decimal is 0.075, and 1 minus, right, because it's saying it's a decay, 1 minus 0.075 is a rate of 0.925. If something is decaying at 0.5%, like not even 1%, just 0.5%, that decimal equivalency is 0.005. And if it's decaying, 1 minus 0.005 is 0.995. If something grows at 1%, the decimal is 0.01. So we're looking at 1.01. If something doubles, it's growing at a rate of 100%, which means your multiplier is just going to be 2, 1 plus 1. And if something triples, it's growing at a rate of 200%, which means your multiplier is just going to be 3. And that's like sometimes a hard concept for students to grasp. Like doubling and having the multiplier be 2 makes total sense, right? 1 plus 1 gives you 2. But sometimes when we talk about tripling, it's a little bit different to think about because we don't really think of 200% and the number 3 going hand in hand. But remember, 1 plus 200% would give us that value of 3. So let's practice a little bit. It says predict the population of bacteria for each time period below if 55 bacteria doubled every hour. So if 55 bacteria doubled every hour, how long would that take after 3 hours? Well, we have to kind of pick out, first off, this 55 is our initial value, right? We start off with 55 bacteria. And the fact that we double every hour means that our multiplier is 2. And if we're talking about hours, we're talking about time, right? So for instance, if we want to figure out how much bacteria we have after 3 hours, we would create y equals some sort of model, right? Our initial value, which is 55, times our multiplier, which is 2, and we would raise it to the third power. Now, all of you guys have the ability to type in a tab of Desmos or use your calculator, and that's sitting next to you in class maybe right now. But you want to make sure that you put parentheses in this because we want to make sure that we cube the number 2 and not cube 55 times 2. There's a really big difference. So we type this into our calculator. We end up getting 440. Okay, what would happen after 6 hours? Y equals 55 times 2 raised to the 6th power. Y equals 3,520. And then after a half hour, so this is super important, right? Like if something's being measured in minutes or seconds and you know that your time in your equation needs to be in hours, it's going to be really important for you to like make that equivalent. Lucky for us, it's talking about a half hour, so we can leave x as 1/2, but y equals 55 times 2 raised to the 1/2 power. And that's just going to happen to be y equals 77.78. So just some food for thought. Like this is more of a thinker question. It's not necessarily, sorry, my chair is squeaking. It's not necessarily something that we need to like super write down like some type of extravagant model. But if you can think about this in your head, then I think we're on a really good track to understanding exponential growth and decay. But if something doubles every 30 minutes and you're asked to find the population of 4 hours, what would you use for the value of n? Like what would you use for like what's changing, right? N is changing. So if something's doubling every 30 minutes, well, think about it. How many 30-minute increments are in 4 hours? The answer would just be 8, right? Like you're evaluating something 8 times. 30 minutes and 30 minutes, that's 1 hour. That's something that happened twice. 30 minutes and 30 minutes now happens 4 times. 30 minutes and 30 minutes now happens 6 times. And then 30 minutes and 30 minutes happens 8 times. So you're evaluating something 8 times if you're looking at it for 4 hours every 30 minutes, right? So just something to think about. It's also really important, and I'll draw a little spot right here. Something to think about as well is how do you think backwards with decay, right? Sometimes students have a hard time with this idea, and we'll definitely talk more about it in class when I come back on Wednesday. But if you're looking at a model where y equals 2 times 0.7 raised to the xth power, obviously, because this is less than 1, this is going to be a decay. But what is the decay rate, right? What is the decay rate? Well, you're looking at this idea of 1 minus x gave you 0.7. Like if we were working backwards like we did up here to figure out what the decay rate actually is, like what percent is it decaying by, you want to take 1 minus this growth rate. And here's the rate right here, right? Like what is x? So if you work backwards, you would come to find out that x is equal to 0.3. So therefore, we're actually decaying by 30%. And that sometimes is a hard concept to grasp with students, that even though the multiplier is 0.7, we would say that we're decaying at a rate of 30%, because you're not saying that you're gaining 70% of an item, right? Like you're losing 30% of that value. So just something to think about, and we'll talk more about it. But so now I'm going to leave you to this last example. Okay. I'm only going to do probably A and B, but I would take a look at C and D, check the key to make sure you're feeling good about this. I don't want this video to be like 30 minutes long. That's not fun for you guys in class to sit and listen to this. So let's just kind of talk through how we would attack this problem. I'll do maybe A and B together, and then you guys can finish this off and check the key with that. So it says a population of a small town is 10,000 in 2013. So this is our initial value. And to be honest with you, if it's saying that we have 10,000 people in 2013, we have to view 2013 as year 0. Right? We just have to assume that this is where we're starting, right? And it says that if it grows at a rate of 5.2%, it's really growing at a multiplier of 0.52. So if we wanted to write this model for population, we would say that y is equal to the 10,000 of the initial population times 1 plus 0.052 raised to that x power, right? So for instance, if we wanted to simplify this, it would look like y equals 10,000 times 1.052 raised to the x power. Now, this next question is kind of that idea that we need to view 2013 as year 0. For instance, what will the population be 6 years from now? Well, in 6 years, it's going to be 2019, but we would not plug in 2019 for x. That would be asking in 2019 years from that point, and we only want 6 years from that point. So we would use the number 6. Y equals 10,000 times 1.052 raised to the 6th power. And with people, if you think of like the US Census or any type of data regarding people, you can't have a third of a person or half of a person. So you always do have to round up to one whole person. So for instance, we would have 13,555 people in 6 years. Okay. Now, take a look at the difference in directions for the next part. The growth rate now is 5.2% each decade. So that means your X values are going to be measured in terms of decades. So if we're taking a look at A, 2023 compared to 2013 is 10 years. Well, guess what? That's 1 decade. X is 1. 2033 is 20 years, right? From 2013, it's 20 years. So that's 2 decades. X is 2. 2018 is 5 years. That's half of a decade, right? So X is 1/2, right? So I would just take it from there. Definitely check the key to how these notes went. But other than that, once you finish these notes, you are free to then go ahead, show the sub that you finished them, grab the homework worksheet. It is double-sided, but it's only 7 questions, really. Go ahead, work through it. Whatever questions you might have, let's save them and let's make sure we go over them first thing in class on Wednesday. So other than that, I hope you have a really great Tuesday. If I see some of you throughout the day in the hall, of course, say hi. And I'm looking forward to sharing my experiences with the Shadow a Student Day. All right, have an awesome day, and I'll see you on Wednesday. Bye-bye.